Okay, let me start. Um, Hello everyone. My name is Ziwei, and I'm now an assistant professor at George Mason University in US. And today I'm very excited to introduce our work about fairness in recommender system to you. And recommender systems have become very important tools today. They are playing crucial roles in connecting users to important and interesting items, information, or other people on the internet. And in the past decades, we have witnessed the thriving development of recommender systems in both industry and academia, and tremendous efforts have been dedicated to designing and building more and more powerful algorithms or systems to increase the recommendation utility across different applications. And here, the recommendation utility means we want to evaluate how effective a recommendation algorithm or system is, and typically the utility is to count how many interactions users provide given the recommendations provided to the users, like the user's behavior of clicks, views, purchase, and so on. And usually the more interactions from the user given the recommendation, the higher utility we achieve by the algorithm or the system. And due to this thriving development of recommendation techniques, today recommender systems are basically everywhere, and they are changing every aspect of our daily lives. For example, we rely on recommender systems to find products to purchase, to meet new friends in the social network, and to find movies or music to relax. And they can also help us to keep healthy, to build professional development, and to keep being aware of what's happening in the world. So with such wide usage, these recommender systems can exert strong but often unforeseen influence on the society in terms of many different aspects, like cultural, politics, or even social justice. And sometimes this influence can be detrimental. And here I show you some examples. The first one is that it has been widely reported that machine learning-based recommendation algorithms or systems can produce bias against women in job hunting and publication sales. And the recommender systems can also expose children to inappropriate content in video streaming platforms. And the recommender systems in social media and news platforms can even intensify the so-called intellectual segregation and societal or political polarization. So it is very dangerous if we advance the development of recommender systems while being blind to these potential risks and harms from the recommender system. So our ultimate goal is to lay the foundation for new responsible recommender systems. And we aim to identify, analyze, and address the potential risks and harms in recommender systems so that we can provide fair and unbiased recommendation to people and the society at large. And here, responsibility is actually a very big umbrella. Under it, there are many topics. So in this talk, I will mainly focus on fairness, and there are actually other problems we may need to take care about, like bias, security, privacy, and explainability. So my message I want to share here is responsible recommender system is a big topic. And in this talk, I will only touch the fairness part of the recommendation or the responsibility. So today I'm gonna introduce two of our works. One is about the fairness for items in recommender system, and the second one is about the fairness for users in recommender systems. So the topic of fairness for items in recommendation is to study how to fairly recommend different items or item groups so that there is no items or item groups are under-recommended. And this is very important in many different scenarios in the real world application. For example, today, many companies, the recruiters in many companies, they rely more and more on automated systems to find candidates to hire or to interview. So it is very important for us to ensure that candidates from different demographic groups are fairly treated by the recommender system. And we also want to ensure that news recommender systems or social media recommender systems are neutral and objective towards different political ideologies or different topics. Or in social, in a more general shopping platform, we also want to maintain certain degree of fairness between big companies versus new entrants for the sake of economic sustainability. And there are many other examples, and all of these real-world examples about fairness in recommendation showing us that it is very urgent and exciting to study and maintain the fairness for items in the recommender system in different scenarios and applications. And in this work, we take the Twitter expert recommendation task as the motivating example to study the recommendation fairness for items. The idea here is that we want to, in Twitter or other social media platform, we want to recommend some users who have some special domain expertise or domain knowledge, and we want to recommend those experts to normal user who want to follow those experts for some information and knowledge about certain domains. So we collected the interaction data between normal users and the experts from Twitter, and then we used the recommendation model, the matrix factorization model, or MF for shorted, which is a foundation for most modern recommender systems. And we want to use this algorithm to conduct our experiment for the expert recommendation. And the main idea of MF is to learn the low dimension latent factors, or you can say embeddings, for users and items. And for this specific example, the items are expert. So we want to learn the embeddings for users and experts based on the historical user-expert interaction data. And then we can predict the user-expert relevance by dot product of the learned user embeddings and the expert embeddings. And the learning of the embeddings can be guided by a loss function such as mean square error loss. And with this MF model, we conducted the expert recommendation experiment with our Twitter data. And from the experiment, we observed that in our crowd data, the distributions of followed experts of different genders and races are very different. And in the generated recommendations from our MF model, the distribution is even more skewed, which means that experts from minority groups like women or people of color have very low chance to be recommended in this expert recommendation problem. And such unfair result certainly hurt diversity, equity, and inclusion in this platform or other social media platform. So this motivated us to think about how can we enhance the fairness in this expert recommendation task for experts of different genders and race. And to achieve this, we need to answer two questions. So first, what is a fair recommendation in this specific example? Or what's the definition of fairness we want to maintain or study? And the second, given the definition of fairness, how can we have a good model or method to enhance the fairness for the experts? And to answer the first question about the definition of fairness, we follow a previous work. We adopt the score-based statistical parity to define the recommendation fairness in this work. And concretely, the score-based statistical parity is to require or ensure that the prediction, which is the predicted score from the model like MF, should be independent to the sensitive attribute or the group labels like female, a male, or other groups like race. And in other words, we want to have the same predicted score distribution from the model for different groups. So that's the definition of fairness we want to study and enhance in this work. And to achieve this score-based statistical parity, we proposed the fairness-aware recommendation algorithm, FAR for short. And in the following, let me introduce how does this algorithm work in order to enhance the fairness for experts. And in this slide, I show you the conventional pipeline, how we generate recommendations by the MF model. So at the beginning, we will have the user expert interaction data represented by a matrix. And this data, we assume it is skewed or biased, which means if we are considering female versus male, then maybe there are more interaction feedback for male compared to a female expert. And then we use the MF model to train or to learn the user embeddings and the expert embeddings. And at the end, by dot product of these two embedding matrices, we can reconstruct the matrix for users and experts. And this completed matrix is the recommendation result we are gonna use for recommendation. And because there is no specific step for enhancing the fairness, so we can assume the recommendation result in this pipeline is unfair. And the reason why we will get unfair result in this method is because that there is some information about the sensitive attribute or the group label like gender or race in the learned user embeddings and item embeddings. And we call this information the sensitive information. Then given this, our intuition of our model is that if we can remove this sensitive information from the learned user embeddings and expert embeddings, and then by dot product of the purified embedding matrices, then we can get a fair recommendation result at the end. So our ultimate goal is to remove those sensitive information from the learned embeddings. Then to do this, there are two steps we need to do. The first step is we want to explicitly insert the sensitive attribute into the expert embeddings. Like if we're gonna enhance fairness for gender, like female versus male, then we explicitly insert the gender attribute for expert into the embeddings. Like if the first expert is a male, is a female, then we have 0 at the male dimension and 1 at the female dimension. And like if the second expert is a male, then we have 1 at the male dimension and 0 at the female dimension, and so on and so forth. So we can insert the gender attribute for all the experts into the embedding matrix. And because these two dimensions, they are exactly the sensitive attribute, so we can say these two dimensions and also the corresponding two dimensions in the user embeddings, they are exclusively related to the sensitive information, like the information of gender. But for those remaining dimensions, there's still some residual sensitive information about the gender in them. So the next step we want to do is to further put an orthogonal constraint on those remaining dimensions in the expert embeddings so that they are orthogonal to the sensitive attribute or to the sensitive dimensions. And by this orthogonal constraint, we can make those remaining dimensions free of the sensitive information because they are orthogonal to the sensitive attribute. And then during the inference time, we remove those two sensitive dimensions, and we only use those non-sensitive dimensions to do the dot product and reconstruct the matrix. And because there is no sensitive information in those dimensions anymore, then we can say the final reconstructed matrix is unbiased or fair recommendation result. Okay, so this is the intuitive idea about our algorithm. And here I want to highlight that there is a advantage of our algorithm, which is that it can easily handle the challenging multi-attribute and the multi-category scenario that previous work cannot easily handle. So the multi-attribute scenario means sometimes we may want to enhance fairness for multiple attributes at the same time. Like we may want to enhance fairness for both gender attribute and race attribute. And for some of the attribute, there could be more than 2 categories. Like for gender, there could be more than 2 categories. Instead of female and male, there could be more different categories of gender. And for race, it's more straightforward. There definitely are more different race under the category, under the attribute of race. And for previous work, it is very difficult for them to handle this challenging multi-attribute and multi-category scenario. But for our algorithm, it's very simple. What we need to do is to explicitly insert the sensitive attribute value for all the attributes we care about into the embedding matrix. And for multi-category attribute, we just have more than 2 dimensions instead of the 2 dimension for the binary attribute. And then we want to put the orthogonal constraint for the remaining dimensions for on all the sensitive attributes we care about, and everything else is exactly the same as I introduced in the previous slide. And by this, we can handle the multi-attribute and the multi-category scenario. Okay, that's all about the algorithm. And now let's see some experimental result to show the performance of the algorithm. And in this experiment, we need to consider two different aspects of the performance. One is the recommendation accuracy or utility. And here we report F1 at K, which is a ranking evaluation metric. The higher, the better. And for the fairness, we report the KS statistic, which is to calculate the difference between two distributions. And here, based on the fairness definition of statistical score-based statistical parity, we want to make the score distribution for different groups to be as similar as possible. So here we calculate the KS statistic between the score distribution for different groups. And the lower the metric is, the smaller the difference is, and the more fair result we get. So for this fairness metric, the lower the better. And in the experiment, we consider the multi-attribute and multi-category scenario. We consider gender and the race at the same time. And for gender, we have female versus male. And for race, we have 3 different race groups. And of course, we can extend it to more different groups and even more attributes. And on the left-hand side, we compare the recommendation utility between the original MF model and our model. So you can see our model drops the recommendation utility a little bit compared to the original MF, which is doing nothing for fairness. And on the right-hand side, we show the KS statistic, which is, again, to calculate the difference for this score distributions. And we compare African American versus white people, and Asian versus white people, and female versus male. And we can see for this fairness result, the lower the better. And we can see compared to the MF model, our algorithm can enhance the fairness or reduce the unfairness to a great extent. The KS statistic is very, very low for those different comparisons compared to the MF model. So by this result, we can say our algorithm drops the utility a little bit, because usually there will be a trade-off between accuracy and fairness, but we enhance the fairness to a very great extent. So in sum, in this work, we study the score-based statistical parity fairness for the item recommendation, and we propose an embedding intervention algorithm to enhance the fairness, and we empirically show that our algorithm can enhance the fairness for the challenging multi-attribute and the multi-category scenario. And by this work, we learned that the recommendation algorithm can deliver unfair recommendations to different items or item groups. Then a natural next question would be, what about users? Will the algorithm treat different users differently? And this question is often overlooked by previous work. So to answer this question, we conducted a simple movie recommendation experiment. Here we use the widely used movie lens dataset, and we conduct some recommendation experiment. And in this slide, we manually pick 5 users, and among them, 3 of them share similar preference for blockbuster movies, who are kind of the majority type of users in the whole dataset. And we call them, or we consider them, as the mainstream users in terms of their preference. And there is 1 user in this slide who prefers classic silent movies, and another one who prefer the award-winning movies of late 80s. And both of them are relatively niche or minority in the whole dataset in terms of their preference. And then with these 5 users, we conduct we train a recommendation model by the dataset, and we show the recommendation utility by the model for these 5 users. And we can observe here on the right-hand side of this slide, we can see that the recommendation model produce much higher utility or accuracy for mainstream users compared to those two niche users. And we call this difference between mainstream users and the niche users the mainstream bias, or can generally say it's a one type of unfairness for users in the recommender system. So next, I will introduce what we learned about this mainstream bias and what we proposed to fight against this mainstream bias for users. So concretely, in this work, we aim to mitigate this mainstream bias for users in a recommendation algorithm. And to achieve this, there are three key challenges we want to answer or address. The first, how can we distinguish the mainstream and niche users in a data set or in a recommender system? And second, what impact the degree of mainstreamness has on the recommendation utility for the users? And the last, to debias, how can we improve the recommendation utility for niche users without decreasing the utility for mainstream users? So that's the ultimate goal of debiasing. And in this work, to address the first challenge, we propose three different methods based on outlier detection technique to indicate the mainstream level for users so that we can differentiate mainstream users and niche users. And then for the second challenge or question, we conduct an empirical study to show that a widely used recommendation algorithm can produce severe mainstream bias among users. And at last, to debias, we explore both global and local method and propose a so-called local fine-tuning algorithm to effectively alleviate this mainstream bias. And in the following slide, I will introduce these three parts one by one. And first, let's talk about how can we evaluate the mainstream level of users to differentiate mainstream user and niche user. And the goal for this part is to have some method to calculate a mainstream score for a user. And we denote it as MSU for the user U to indicate the mainstreamness of the user U. So the higher the score, the more likely the user U is a mainstream user. So that's the goal we want to achieve. And to do this, we propose three different methods based on outlier detection technique to calculate this mainstream score. So we can kind of consider mainstream users are normal data in a data set, and the niche users are outliers in the data set. So by outlier detection, we can identify them and assign each of them a score to indicate their mainstreamness. And we propose the similarity-based algorithm, distribution-based method, and the last one is deep SVDD-based. And due to the limitation of time today, I will not introduce the details about the first two. And they are actually very intuitive and straightforward. If you are interested, you can read our paper. So I just want to briefly explain the deep SVDD one, which performed the best in our experiment. So this method is based on the deep learning outlier detection model, the deep SVDD. And the main idea of deep SVDD is to transform the data samples from a data set into a mapping space by a deep neural network, so that most of the data samples are inside a hypersphere in the new mapping space. And the samples outside the hypersphere in the mapping space are considered as outliers. And then we can calculate the distance between each sample to the centroid of the hypersphere as an indicator for their level of outliers or level of mainstreamness. So if we apply this deep SVDD model to the user records, historical interaction records, and we can expect that mainstream users will have short distance to the center of the hypersphere created by deep SVDD in the mapping space. So we can use the negative distance from users to the center of the hypersphere in the new mapping space as the mainstream score. So the smaller the score, the more likely the user is a mainstream user, and the larger the score, the user could be a niche user. So that's the idea, and the formula is represented by this expression equation in this slide. And based on the calculated mainstream score, and I only introduced the deep SVDD, but it's the same idea for similarity-based and distribution-based. All of them will just assign a score for user, and the larger, the more likely it is a mainstream user. And based on this calculated mainstream score, we can divide users evenly into 5 groups with increasing mainstream levels, which means we sort all the users based on their mainstream score in a increasing order, and then we evenly divide them into 5 parts. Then the low group means the 20% of users who have the lowest mainstream score from these 3 algorithms. And the high group means the 20% users with the highest mainstream score from these algorithms. So we divide user into 5 groups evenly. And then we can train a recommendation model by this data set, and we report the average performance for each of the group and compare the average performance across them to show whether there is a mainstream bias or not. And in this experiment, we use the variational autoencoder, VAE, which is kind of the state-of-the-art algorithm for recommendation. And we still use the movie lens dataset, which is a movie recommendation dataset. And we report an NDCG at 20, which is a more, I would say, a better ranking evaluation or recommendation evaluation metric compared to the F1 at K, which we see for the first work. And then from this result, we can see generally users with higher mainstream score will get higher recommendation utility. Oh, sorry, I forgot to mention the NDCG is the same, the higher the better. Okay, so we can see from this table, no matter what mainstream score calculation method, the pattern is the same. The user with higher mainstream score or higher mainstream level get better recommendation result from the model. And you can see if we compare the low group and the high group, it's kind of the NDCG performance is more than doubled compared to the low group. So this result shows severe mainstream bias for the VAE model. And actually, we conducted experiment with other widely used recommendation algorithms. All of them show similar pattern. That mainstream user get a higher recommendation result from the model. So this observation of the bias motivated us to think about how can we effectively debias or address this problem. And the goal of debias is to improve the utility for users with low mainstream scores or niche users. And at the same time, we also want to increase or at least preserve the recommendation utility for the mainstream users. So we do not want to, in order to increase the utility for niche users, we have to decrease the utility for mainstream users. So no, that's not what we want to do. We want to increase all of them, or at least preserve the similar level of utility for the mainstream users. So that's the goal we want to achieve in order to debias. Okay, so in the following, I will show you our exploration of both global method and the local method in order to achieve this debiasing. And based on our understanding and the exploration of this problem, one major reason we hypothesis why we can observe this unbiased mainstream bias in our experiment is that typically we train a recommendation model by a loss function averaging over all users. However, based on the definition of mainstream users, who are the majority users share similar preference. So we can say there are more mainstream users in the data set compared to niche users. So if we do this averaging based loss function, then the model will be trained to focus on improving the utility for mainstream users because they are the majority, while overlooking the performance for niche users. So this is one major reason why we get the mainstream bias. Then, based on this intuition, the global method is to still use one model to serve all the users, but we want to increase the importance of niche users during the model training process. So that's the high-level idea of global model or global method. And in the work, we actually propose two different global methods. One is the one I'm gonna show you, the weighted loss algorithm. Another one is a data augmentation algorithm. But the idea for them is actually the same. We want to increase the importance or appearance of niche users in the training process, either in the loss function part or in the data set itself. And here I just want to show you the weighted loss one, which perform better than the data augmentation method. So the idea is we want to assign a weight for each of the user in the loss function. And by the weight, we can control the importance of the user in the training process. And if it is a mainstream user, then we may want to assign a lower weight in order to decrease the importance because they are already majority in the data set. And we want to make a large weight for niche users in order to increase their importance in the training process. So the formula is written here. And this part, the LVAEU is the original loss function for one user U. And then we assign a weight to this loss for the user, and then we sum up over all the users to be the final loss function. And the weight here should be inversely proportional to the mainstream score of the user. And if the mainstream score is large, then the weight will be small. And we have a beta here to control the strength of the debiasing. And if it's a large beta, then we have a strong strength to debias. If it's small, like if it's 0, then there's no debiasing at all. So this is a very simple idea and algorithm, and it can behave as we expect to improve the performance for niche user. However, you will see later in the experiment, the global model will decrease the performance for the mainstream user. And so it is not what we eventually want for debiasing. And the reason why it cannot work effectively is because there is another reason of the mainstream bias, which is that the data from users of different preference may be not helpful or can even play negative roles, like if there are conflicts for learning the preference of a target group of users. So if there is a strong conflict between the mainstream user and niche users in the dataset, like they are completely different preference or opposite preference between the mainstream user and niche user, then the global model, which only use one model for serving all the users, may not be able to learn for all of them. Then there will be always a trade-off between niche user and the mainstream user. And then because of this, the global model have to drop the performance for mainstream user in order to achieve increase the performance for the niche user. And this motivated us to think about alternative solution, which is the local solution, local method to debias. The main idea is that we want to consider recommending for each user or each type of user as an independent task and have a customized local model for each user or each type of user. And by doing this, there will be no conflict among different types of user anymore because each of them will have a customized model to serve them. And because they will have their own model, so there is no unfairness between them during the training process because they are equally important during the training since they have their own model to be trained. So this local method can address both of the reasons of the mainstream bias together. And based on this idea, we propose a simple method called local fine-tuning algorithm. And this algorithm is composed of 3 parts, 3 steps, and this is also a very simple method. The first step is we just train a base recommendation model with all the data from the data set. just like how we train a conventional recommendation model as usual, like we train and like how we train the VAE model, which is just a conventional recommendation model without considering the bias. And for the base model, we can also use the global debiased model, like the weighted loss model or the data augmentation method I didn't introduce here. And based on our experiment, we show that if we pick the debiased global model as the base model, it performs better. So then in the experiment experiment section, we just take the WL as the default base model. But you can pick any recommendation model as the base model. And then at the second step, for each user, we will fetch other users who are similar to the target user to build the so-called neighbor user set. So basically, we just for each of the user, we found similar user for them and make them as a user set. And at last, during the inference time, for each user, we will fine-tune the base model for a small number of epochs by only the data of the neighbor user set of the target user. And then we can deliver the final recommendation result for that user by the fine-tuned algorithm. So by these three steps, we can achieve our goal of treating recommending for each user as an independent task using a customized local model. And this customized local model is built by the fine-tuning, the local fine-tuning with the local neighbor user set. So that's the idea about global method and local method to debias the mainstream bias problem. And now let's see some experimental result to show how those different algorithms perform. Okay, and here we still use the movie lens 1 million data set. And in the paper, we actually conducted experiment with other data sets, but here we just show one. And we also use the deep SVDD to calculate the mainstream scores and to divide the users. Based on the score, we divide users into 5 groups, and we report the NDCGR20 or average NDCGR20 for each of the group and compare the value across the groups to show the mainstream bias. The same setup as what we saw before. And NDCGR20 is the metric we use. And for this column, we show the overall performance. And in this slide, we compare the conventional variation autoencoder, so without doing anything for debiasing, versus our global method, the weighted loss algorithm. And we compare their overall performance, and we also show how these two algorithms perform in terms of the mainstream bias. And we can see, comparing WL versus VAE, the WL can significantly improve the utility for the two niche user groups. And the WL kind of preserve the utility for the medium group, but it decreased the performance a little bit, like less than 2%, but it still decreased the utility for the two mainstream user groups. And overall, the performance is increased by the WL model compared to the VAE model, but the improvement is very limited. So that's the performance of the WL, the global method, as I already introduced, that it has to decrease the utility for mainstream users in order to increase the utility for niche users. And then let's see the performance of local method. And before I introduce our algorithm, here I also include a baseline model, the local model baseline. It's called LOCA. It's from another group. It's a previous work, not from our group. And in that paper, the authors, they just try to improve the overall performance of the recommendation result. And they did not discuss the topic of mainstream bias for users. But we think this algorithm actually can work for the mainstream bias. So we involve it in to compare with our local method. So in this slide, let's compare the global method and this local method baseline. And we can see the local method baseline can have even further improve the utility for those niche users. at the same time, it preserve or it performs similarly for the mainstream users as the WL method, which means compared to the VAE model, the local method still decrease the performance for those mainstream users. Okay, so that's the performance of the baseline local method. And we can say this baseline is better than the global method we proposed. And at last, let's see our final algorithm, the local fine-tuning algorithm. And first, let's compare the local fine-tuning algorithm LFT with the VAE model. And we can see, comparing these two, our algorithm LFT can improve the utility for all type of users. And the improvement for those niche users is remarkable. And we can also improve the utility for the most mainstream users a little bit, like 2.7%. And of course, the overall performance is significantly improved compared to the VAE. And then let's compare our local method versus the local method baseline. And we can see overall, our method can perform better, increase the performance over the local. And if we look into those 5 different user groups, our method compared to local can perform better over all the type of users. And for all of them, there is a significant improvement over the local. So that's the fantastic result from our model in terms of the overall performance and the mainstream bias. So in sum, in this work, we proposed 3 different methods based on outlier detection technique to indicate the mainstream level of users in order to differentiate the mainstream user and niche user. And then we conduct empirical studies to show some widely used algorithms can produce severe mainstream bias. And at last, we explore both global method and local method and propose the effective local fine-tuning algorithm to alleviate this bias. So that's all I want to share about fairness in recommendation today, and I'd like to take any question.